Last time we defined the phrase f is a function to mean a conjunction of two things, that f is a set of pairs, and whenever you have two pairs in f with the first coordinate being the same, then it follows that the second coordinates have to be the same. So this is our definition of function. So this is one thing we did last time. And the other thing we did is to prove that if you take the collection of if x is in the domain, if f is a function, if you have a known function, so something that satisfies this property, and you take some x which is in the domain of that function, meaning in the domain meaning there exists some y that gets matched up with x by f. So the pair x comma something is an element of f. That's what this means. The pair x comma something is an element of f for some something as the second coordinate. Then what we proved is that if you take this collection, the collection of those somethings, the possible things that can sit in the second position in a pair that is in f, then this is a singleton. So this was Theorem 49 that we proved. So pretty much the assumption that f is a function guarantees that this have only at most one element, and the assumption that x is in the domain of f guarantees that this set has at least one element. And so when you have both f is a function and x and this set is non-empty, this basically is just a way of saying this set is non-empty, then this has exactly one element. And when there's a unique something that satisfies a certain property, we can give that unique something a name and refer to it. That can be a way of defining something. So if you're in this context where f is a function and x is in the domain of f, then we can give a name to the unique y such that the pair xy is an element of f. In other words, we can give a name to the unique occupant of this singleton. And that name is what shows up in definition 50, the definition of function evaluation. That name is f of x. So let's just go over definition 50. If you have a known function, so this definition has assumptions. You can only apply this definition when you already know these things to be true. F has to be a function, and you have to have a known element of the domain, x. Then what we are defining is this object, f of x. And there are two ways to write the definition. And I give you both ways. One way is very formal and symbolic, which is this. But first, let's look at this less symbolic way. So in this context, by Theorem 49, that thing that we proved last time, there is a unique y such that the pair xy is an element of f. When there's a unique something that satisfies a certain property, we can take that as giving us a way of defining something, of defining a symbol. So here we're defining f of x, f parentheses x, which we read as f of x. We're defining that to be the unique y that makes this happen. So in other words, assuming you are in this context where f is a function and x is in the domain of f, you have x, fx, f of x is in f. And this property of f of x is what defines what it is. It's the unique thing that can sit here and make this true. So this is evaluation. We call this the value of f at x. And if you want a more symbolic way of looking at it, then here's a way of looking at it. Is we've got this thing that we showed as a singleton, the collection of y's that goes with x. And when you have a singleton, then we have this construction that can, the occupant construction, that can extract the one thing sitting inside the singleton. So I'm looking back here at page 60 and 61 in the full notes, not the reference version. Back at this discussion about getting unique things and trying to make definitions using a uniqueness property. Remember, in that discussion we were talking about sort of as this placeholder predicate being green. So what if you knew that there is a unique green thing in the world? How would you use our kind of formalism to refer to it or define a new symbol to mean the unique green thing? And we have two ways of writing it. We can use the occupant construction and say, okay, if we know that there's a unique green thing, then we know the set of green things is a singleton set. So we can take its occupant. And then that G then refers to the unique green thing. But like I told you, the occupant symbol is a made-up thing just for this course. In practice, what people do when they're doing this is they say a sentence like this: let G denote the unique green thing. And then this becomes an allowed way to define something. It's acceptable because it's basically just doing this. So in our context here with defining the value of a function at a point like f of x, I'm sort of giving you these two ways of looking at it. So if you look here, one way is symbolic. I'm saying let f of x be the occupant of this singleton set. And another way, assuming f is a function and x is in the domain of f, is to say let f of x denote not the unique green thing, but the unique thing that makes this true. So the unique thing that fits here to make this statement true. Okay, I think that's enough of a recap. So let's move on to the next result. And you can see the title of this has the essence of pattern. So here we're defining evaluation, and this is the essence of evaluation. So following my convention for titling these things, this suggests to you that you typically would not use this at all. And in fact, this definition is just designed to make this theorem hold, and this theorem is what you would normally use. So let's prove this theorem and make it available to us so that we can go ahead and start studying functions. So the first thing to notice is that it starts with an assumption. If f is a function, then 1, 2, 3. So when you see this list 1, 2, 3 following a then that means it's a conjunction saying if f is a function, then this statement is true, and this statement is true, and this statement is true. But each of these is itself an if-then. So I'm going to break this up into 3 parts where I mush the assumptions together, and yeah, I'm just going to mush the assumptions together for each part. It's just when I'm writing them all together like this, I don't really want to mush them together, because then I'd keep repeating assume f is a function each time. So I'd be like, 1, if f is a function and x is in the domain of f, then blah. 2, if f is a function, then, you know, I'd keep repeating this phrase. So that's why sometimes some assumptions sit outside the numbered list, and sometimes certain assumptions will be moved into the numbered list. Like, for example, the assumption x is in the domain of f. That only appears in 2 of the 3 items, so I wouldn't put this outside the numbered list. Okay, anyway, I'm going to look at these items individually and just mush the assumptions together. Okay, so here's the first part, 51.1, so this one. If f is a function and x is in the domain of f, so that's the if part. If f is a function and x is in the domain of f, then, so I've mushed those assumptions together, then the pair x comma fx is in f. So we'll start by assuming the hypotheses. So assume f is a function and x is in the domain of f. then what? Let's see. So somehow my conclusion, so my goal is this, right? My conclusion somehow needs to involve this thing. So somewhere I'm going to need to use the definition of this thing. And at the moment, that's definition 50. Normally, you wouldn't use definition 50 for anything, but this is the one time we use definition 50 is when we're proving theorem 51, which then, after it's proven, is what you would normally use. So somehow we have to use definition 50 to reason about this object here. So in definition 50, we are told that if f is a function and x is in the domain of f, which is something that's true for us, then what the symbol f of x refers to is the unique element of this set, right? That's what it refers to. So I guess it's pretty much immediate if you use that language that you know, f of x is an element. It's the unique element of this set, so it is an element. But just to stick to being more rigorous and relying on the symbol awk here that I'm using, let me break down using Theorem 49 what this is. So by Theorem 49, which we can apply, Theorem 49 requires f is a function and x is in the domain of f, which we have, so we can apply Theorem 49. By Theorem 49, this is a singleton. Okay, what does that mean? So this being a singleton idea, to be a singleton is to be singleton something, right? This is the definition. To be a singleton is for this existentially quantified statement to hold. S is a singleton means S is singleton something. So we can get, this is existential instantiation, we can get a, let's call it Z, such that that set is actually just singleton Z. Now we can make use of the fully symbolic formal version of definition, whatever it was, the definition of function evaluation. Sorry, definition 50. So I want to use this. This is what f of x equals. This is what it's defined to be, the occupant of this set. And I now have written this set in the form of a singleton. So then we have, let's see, so f of x by, now here I'm using definition 50. By definition 50, f of x is the occupant of that set. Like that. And then now I'm using Theorem 4, I guess, to replace something by something that it's equal to. So that's the occupant of singleton Z. And then what is the occupant of a singleton? Is the thing living in there, the one person living in there inside the singleton. So this is by, probably it was essence of occupant or something like that. The fundamental fact about occupant that one needs to know, Theorem 27. So f of x is that one, whatever is that name we gave to that one thing living in there, that's what f of x is. Okay, therefore, since f of x is this thing, therefore, this set, the set of y's that go with x, is, so we said it was singleton Z, right? But now we have a new name for Z. it's f of x. F of x equals z. So I'm going to write this, but with the z replaced by something that it's equal to. Now, what was our goal again? Our goal was to prove that this pair is in F. We seem to be there pretty much. F of x is definitely an element of singleton f of x, right? So it's an element of this left-hand side then. So since f of x is in singleton f of x, since it is equal to itself, right? And this is apparently another way of writing this. We have, sort of by axiom 5, breaking down what it means for something to be in here, we have that this holds with the y replaced by f of x. So we have x comma f of x in F. And that was the goal, right? That's what we needed for this theorem. So I'm going to end that theorem, I'm going to end that proof there. So that was only part 1 of theorem 51.1. But actually we might be able to, a lot of good work was done in this proof, so we might be able to merge different parts in the same theorem. So part 2 says something about when the pair xy is in F, then such and such happens. But, it also has well, no, I think it'll be confusing to try to merge the proof of part 2 into this one. Let's start a separate proof and see what works. Part of what might be confusing is that in part 1 we have the assumption x is in the domain of F, and we use that to do things. In part 2 we do not directly have that assumption. Okay, so here's part 2 of theorem 51. So now I'm assuming f is a function. That's because that was one of the global assumptions for the whole theorem. And then instead of assuming this, I'm assuming this. Xy is in, the pair xy is in F. Then y equals f of x. Okay, so proof, and the proof will start by making the assumptions in the theorem. So I'm just going to duplicate this and be a little bit lazy. There, and no conclusion. That's what we're trying to prove now. So assume f is a function and the pair xy is an element of F. Then my goal is to prove y equals f of x. If I'm going to do anything with f of x, then I need to use the definition, right? What's available to me now is the result from part 1 and the definition. So one way to go is to try to, so here's a first thought. After doing theorem 51.1, a first thought is, look, if this pair is in F, then that means x is in the domain of F, right? Because x comma something is in F. So we are in a situation where x is in the domain of F. So then we are in a situation where f is a function and x is in the domain of F, and so this is a singleton. And so we can pull the same trick that we did back in theorem 51.1, where, we got a z so that this thing is singleton z, and then we wrote f of x as the occupant of that singleton. And so this was this, and it seems like from there we can do this theorem. So that works, but it actually sort of repeats a lot of the work we did in the previous theorem, and there's an easier path. So here's the easier path that's now available to us. Directly using that f as a function. So first, let us actually point out, so the goal with this different approach that I'm suggesting is to make use of the previous part and the fact that f is a function. So you'll see. So first, we do need that x is in the domain of F. we need to show x is in the domain of f in order to apply the previous part, since it says this. X is in the domain of f. So let's just point that out. Since this is an f, we have this existential generalization, right? X comma something is an f. Thus, x is in the domain of f. Now we can apply, now we have f as a function, here f is a function, and x is in the domain of f. So now part 1 of the theorem applies, and we conclude that the pair x comma f of x is an f. Great. Now my goal is to prove that y equals f of x, but look at the situation I'm in. F is a function. Here is a pair in f, here is another pair in f, and the first positions match. So then by the definition of function, remember at the beginning we in our recap at the beginning, we were saying this is part of the definition of function. A set of pairs where whenever two pairs are in it and the first positions match, the second positions must also match. So we can actually use that fact now. Since f is a function, and the pair xy and the pair x fx are both in f, we have y equals f of x. And that proves Theorem 51, Part 2. Great. So the way I think about it, 51 Part 1 is sort of saying when f can be evaluated at x, meaning when x is in the domain of f, then x f of x is a pair in f. And part 2 says sort of it's the only one. F of x is the only thing that works. So part 2 is another way of stating that uniqueness, is if you had x, y in there, then y is f of x. So this is like a statement of the defining property of f of x, and part 2 here is like a statement of uniqueness of that, of f of x with respect to that property. Part 3 is actually just merging parts 1 and 2 together. So it says if f is a function and x is in the domain of f, then a pair like xy is going to be in f if and only if y is the thing that we call f of x. So this is the fundamental thing to understand to get how our system is modeling the idea of functions, is that these pairs are representing input-output associations. So we usually think of this as kind of input and that as the output. Okay, and proof. So assume that f is a function and x is in the domain of f. Then we need to prove this double arrow. So here, suppose that the pair xy is in f. Then I have f is a function and the pair xy is in f, right? And part 2 was when that happens, and when f is a function and the pair xy is in f, y equals fx. So that's it. So by part 2, y is fx. In the other direction, assume y is fx. Then what are we trying to prove? That the pair xy is in f, right? But y is f of x. So our goal, let's re-express our goal. We must prove that the pair x, comma, and then instead of y, let me write down something y is equal to, since that's equivalent, fx. is an f. But I'm in a context where f is a function. Sorry, let me put it here. F is a function and x is in the domain of f, which is exactly what's needed to apply part 1. And that does give me the thing that I want. X comma fx is an f. By part 1, we have this, let's say. We have this thing that we must prove. So we are done here. All right, so I'll end it for this video. And in the next one, we can look at some examples and other ways of defining functions, other than just, writing down a list of pairs. So we'll look at lists of pairs, but we'll also look at, the typical formula kind of way of doing things.